Okay, here we go. What you've been waiting for all year, nuclear charge and electron shielding. Okay, so why are these things important in chemistry? Well, they help explain this question right here. How can we explain the observed periodic trends in properties like atomic size, ionization energy, and something that we'll get to in the next unit on bonding, electronegativity. So, um, what you've read about recently is how the size of atoms change as you go across the periodic table from left to right and as you go down the periodic table. And I'll just kind of spoiler alert, as you go from left to right, the dimension of atoms decreases generally. There's a few little hiccups, along the way, but in general, atoms get smaller as you go toward the right, and they get bigger, generally, as you go top to bottom. And we need to have a good understanding of how that happens. And to really get a deep understanding and understand some of the nuances, we have to start way back with Coulomb's law, which is kind of interesting. It's a really good thing to know if you haven't heard of it. Coulomb was a Frenchman back in the 1700s, and he was a very good scientist in his day. And one of the things that he helped sort out in science was some of the characteristics of charged particles, especially the forces that acted on charged particles when they interact with each other. So, for example, let's say we have two particles. All right, one has a positive charge, the other one has a negative charge, and you can have different degrees of charge. So the number just tells you that this one has a 1 unit of positive charge, the other particle has 1 unit of negative charge. Okay, and when charged particles, are especially when they're in close proximity, they definitely exert a force on each other. And you guys know the saying, opposite charges attract. Okay, so these two charges in particular would be feeling forces of attraction to each other. They're drawn to each other. Conversely, if we had two of the same charges, if we had two positive charges or two negative charges, they would repel each other. But for this example, we're going to talk about a case where they have opposite charges. Okay, now that's kind of a qualitative description of this situation, but we need to come up with a more quantitative description, and that's where Coulomb came into play. So Coulomb was able to figure out that if you know the charge on each particle and you know the distance between them, then there's a very well-defined relationship between those two properties, that is charge and distance, and then the force that's operating between them. And this is it takes the form of an equation. And so in the equation, the Q's represent the charge. So it's the quantity of the charge on each particle. So Q sub 1 is the charge on particle 1, and Q sub 2 is the charge on the other particle. And K is just a proportionality constant. Don't worry about that for now. And the distance is very straightforward. It's simply the distance between the two particles. But it's not just the distance, but it's the square. So if you were to paraphrase this formula, you would say that the force that exists between two charged particles is proportional to the product of their charges, and inversely proportional to the square of the distance. Okay, so let's just kind of get a feel for this. All right, so let's say that this, I'm going to use a little, a little bar here, and the height of the bar is going to be proportional to the force that is being exerted between these two charged particles. All right, so let's just say for this distance and for one plus charge and one minus charge, that's the force. Okay, so now let's change the distance. Okay, so we're going to move them closer together so that the distance is only half as far as it was. Okay, so if we cut the distance in half, what that would do to the force is it would quadruple it. Okay, because it's a squared relationship. So the force that's being exerted between these two particles now is 4 times what it was before when they were twice as far apart. Okay, now let's maybe twiddle with the magnitude of the charge button here. Okay, so if we double the charge on just this one, what's that going to do? Well, you can see, since the force is proportional to the product of the charges, if we double one of the charges, we're going to double the force, right? So the force is going to go from here to there. Okay, and then we could get even crazier. We could say, well, what if we take this charge and we triple it, all right, and we make it +6? Okay, so if we triple the charge, you got it. It's going to triple the force. Okay, so this is just a very quick and dirty way of kind of giving you a feel for what Coulomb's law is about. Okay, so the important thing is you realize that when you have two charged particles, I just want you to have a sense of the relationship that kind of relates that force with the magnitude of the charge and the distance. Okay, so what does that have to do with things like atomic size? Well, consider an atom of lithium. Okay, now let me just pause for a second. If you're watching this video, please make sure you have a periodic table at the side here so that you can refer to it as we go. Okay, all right, so here's lithium. You've got two 1s electrons, and then here's the valence electron in the 2s. There are 3 protons in the nucleus. Okay, so that's what I'm indicating here with the number. And as you go, starting with lithium, if you go to the right in period 2 of your periodic table, the next element that you encounter is beryllium, right? Atomic number 4, and you have now, in going from lithium to beryllium, you've increased the magnitude of the charge here, and so the force of attraction between the nucleus and the electrons is now greater. Okay, and so we kind of know that from Coulomb's law. And if we keep going to the right, next is boron. Now we have an even more positive charge packed into this small nucleus, and so the force of attraction is even greater. And what that does is it's pulling on the electron, the electrons out here, and because that force of attraction is greater, it's causing the electron shells to contract a little bit. Okay, here's carbon. There's even further contraction, and then if you go all the way, to fluorine, you'll see it's even more. Okay, so here I'm just going to go through the same sequence, and I'm just going to put a little text up here just to kind of summarize what's going on. So increasing positive charge in the nucleus leads to stronger electrostatic attraction between the electrons and the protons as we go toward the right of the periodic table, and that leads to contraction of the electron cloud, right? Because it's because you've got more positive charge in there. It's like kind of like having a stronger magnet, and it's pulling the electrons in more strongly, and it makes the atomic radius contract. Okay, so let's look at this. Let's try to connect this to the periodic table. All right, so right now I've got a little shaded area here on lithium. Here's the situation, and as we go across that periodic table, there's boron. The radius is getting smaller. Okay, now We talked earlier about the fact that atoms get larger as you go down the periodic table, and that's pretty intuitive. But trying to explain why atoms get smaller as we go from left to right, that's the trickier concept. And so I just want to make sure that we're going through that step by step. Okay, so this summarizes the trend, right? So as we go from left to right across the periodic table, size generally decreases. Okay, now what about going down the table? Okay, well, let's start with helium. So here's helium, 2 electrons right here. Okay, and what I've done here is I've just, here I was showing the 2 electrons explicitly. Now they're just implicit in that first shell. And then when we go to period 2 and we add the 3rd electron, now you could say that that valence electron is shielded from the nucleus. Okay, and in fact, the valence electrons of all period 2 elements, as we'll see in a moment, are shielded by 1 energy level of electrons, right? Because you see you've got these 2 electrons in the 1s orbital. And so, excuse me, and so in a sense, these electrons that are going to be, any electron in the 2nd principal energy level is, kind of protected from the nucleus by that 1s shell, okay? And so we can go on. So if we go down to sodium, okay, now that 11th electron, which is the valence electron on sodium, that electron is now shielded from the nucleus, not by 1, but by 2 energy levels of electrons. Okay, so and then if you go down to potassium, okay, now you've got three main energy levels that are shielding the valence electrons. Okay, so in general, the shielding is increasing as you go from top to bottom. And I hope, let me back up a little bit. I hope that I'm making that reasonably clear. Okay, there's lithium, there's sodium, so kind of watch the model there. So every time you go down another period in the periodic table, you're adding another layer of electrons between the valence electrons and the nucleus. Okay? Therefore, shielding increases, and that, my friends, is why size, atomic radius, increases as we go from top to bottom. Okay, so just to kind of wrap it up here, this summarizes the overall trends in atomic size. Okay, so we've seen that the atoms get smaller as we go from left to right, and I hope that now, with a little, having gone into a little bit of detail on electrostatic force and Coulomb's law, I hope that you have a little better sense of why the atoms contract going left to right. And then I think, certainly the observation that atoms get bigger from top to bottom, that's pretty straightforward. Okay, thank you very much.